Okay, so we're live already. Good. Well, so hi everyone to this online Rencontres Theorician talk. So today it's our pleasure to have Ben Krabs, and Ben will be telling us about slow scrambling in extremal BT set and microstate geometries. So Ben, stage is yours.
Okay, well, thanks a lot for the invitation. So this talk will be about a paper that appeared recently with Marine de Klerk, Philippe Hacker, Kevin Gian, and Charles Rabideau. And it's actually a project that grew out of a workshop that Nick and Yosif are organizing at Saclay in June, I believe. So matter of recent debate is what is the nature of black hole microstates? Like, do these microstates of black holes have horizons and regions beyond the horizon? And this is a picture that appears, for instance, in recent discussions of reproducing the page curve from gravity computations. Or do microstates have a rather different nature? For instance, would many or all of them correspond to smooth geometries without a horizon? So if microstates correspond to horizonless geometries, one would expect that when one computes observables in these geometries, they should approximate those in black hole backgrounds, but they should also deviate from them when you probe with sufficient accuracy. So to give a few examples, there have been various papers on the approximate thermality of various probes in gravitational microstates, often using the ADS-CFT correspondence. There's been a discussion of an analog of Hawking radiation in microstates of certain non-extremal black holes. And there's been recent work on thermalization and revivals of retarded two-point functions in microstates of extremal black holes. So in this talk, I will talk about another probe of such microstates, namely an observable that is related to quantum chaos. So let me first say a few words on black holes and quantum chaos. So black holes are chaotic objects, and this chaos underlies the thermal behavior of black holes. There are several manifestations of that. First of all, if you excite a black hole, it will relax to thermal equilibrium. And second, there is a sensitivity to initial conditions that is very familiar from classical chaos. So extending notions from classical chaos to quantum mechanics is non-trivial. For instance, in classical chaos, one often refers to phase space trajectories that diverge exponentially. In quantum mechanics, you don't have precise trajectories in phase space. Also, the evolution equation in quantum mechanics is linear. So if you measure distances by taking inner products, there will be invariant under time evolution as opposed to growing exponentially. So one needs some more sophisticated ways of generalizing notions of classical chaos to quantum mechanics. Now, if you can work in a semi-classical approximation, one can try and replace the Poisson brackets that appeared in the previous formula by a commutator. And one can consider the growth of this commutator squared, that's to avoid phase cancellations, in some thermal state. And you can imagine these operators to have disjoint support to begin with, so they would commute at time zero. But then as one operator evolves in time and thereby spreads over the system, at some point they will start having a non-zero commutator, and that time dependence you can track. Now, it turns out that if you study this commutator squareds in these quantum systems in some semi-classical limits, you typically find two exponential behaviors. And I borrowed this picture from a paper by Polchinski. A first exponential behavior corresponds to the so-called Ruel resonances, which describe the exponential saturation. So in this case, we're talking about a 4-point function, but this exponential saturation would also be there if you computed, for instance, retarded 2-point functions. And under the ADS-CFT correspondence, these Ruel resonances are mapped to the quasi-normal modes of black holes. Now, to see the other exponential behavior, which is this early time Lyapunov growth, you have to look at other observables. And in particular, under the ADS-CFT correspondence, this Lyapunov behavior is mapped to the redshift of a probe that falls into the black hole. So here is the redshift factor. Beta is the inverse temperature. And one thing to note is that this redshift factor is determined precisely by the inverse temperature. So it corresponds to the surface gravity at the horizon of a black hole. On the other hand, the quasi-normal mode frequencies are typically proportional to the temperature, but there are some order 1 factors by which they differ. And this is because the quasi-normal modes, if you compute them, they correspond to what happens outside, say within a few Schwarzschild radii of the black hole. So from this point of view, it seems that this Lyapunov growth actually probes properties at the black hole horizon as opposed to in some region around it. So if you look at times that are large compared to the inverse temperature, and you study this normalized commutator squared, then you can convince yourself that it will be approximately equal to 1 minus the real part of this out of time order correlator. This is because if you expand this commutator squared, you will have this out of time order terms. You will also have some other contributions, for instance, V, W, W, V, but those will just give the same as the disconnected contribution in the denominator. That's because if you act with V of 0 on some thermal states and then you wait a few thermal times, the system will thermalize, and therefore the 4-point function will reduce to a 2-point function times the norm of the system you of the state you created. So if this Lyapunov growth reflects what happens at the horizon, it's very interesting to ask what would happen in microstate geometries that don't have horizons. Now, a reason why this is not completely trivial to study is that microstate geometries have been mostly restricted to extremal black holes, and those have 0 temperature. So this Lyapunov exponent that we saw before, which was proportional to the temperature, would actually vanish. So therefore, what we will do in this talk is computing out of time order correlators for extremal black holes and some of the corresponding microstate geometries. As Josif was emphasizing in this workshop I just mentioned, is that this is presumably much easier than constructing microstate geometries that are very similar to black holes for non-extremal black holes. So that's the exercise we did in the paper I'm telling you about today. All right, so that was my brief introduction. So next I will tell you about how one computes these out-of-time order correlators, and I will mention a geodesic approximation that we've been using in our work. After that, I will discuss the OTOC in extremal BTZ geometries, and then I will move on to microstate geometries, and then there will be some brief discussion at the end. By the way, if you have any questions, feel free to interrupt us at any time. We should have more than enough time for what I have to say. All right. So first, let me tell you a little bit about CFT computations of OTOCs in actually holographic two-dimensional CFTs. This is work from a few years ago by Roberts and Stanford. So let's take two operators, V and W, both have large conformal dimension. And for simplicity, we assume some hierarchy between the two conformal dimensions. So to be precise, you need to regulate the 4-point function, because if you inserted the two V operators at the same position, there would be some UV divergence. So we take some imaginary time shifts of the various operators, and we normalize the OTOC. And then by using conformal block expansion and assuming that it's the vacuum block that dominates, you get the expression on the right-hand side, where these epsilons have to do with the UV regulators, and you recognize this exponential of 2 pi over beta times time. So this CFT has a central charge C, which we take to be very large because we're in a holographic CFT. And if you do a 1 over C expansion and you take the first non-trivial term, you find this exponential behavior that we saw before in the commutator squared. Now, at some time ts, which we'll call the scrambling time, this 1 over C correction will start competing with the constant term, the 1 here. And this scrambling time grows with the separation of the two operators that you are considering. And also it grows logarithmically with the central charge of the CFT. So the scrambling time is a time where one imagines that the information of a perturbation has spread over the system and is therefore not accessible by doing local measurements. You would need to have access to the whole system to do measurements.
Ben, just a quick question. Isn't it alarming that all of this is so sensitive to the regulators that you've inserted, these epsilons?
Well, yeah, so I think in principle, what you would imagine to do is spread the insertions over some thermal scale, for instance, and then do the computations. But it's true that that here, these prefactors of the exponential growth depend on the details of the regulator. I think what is important is that the exponent does not depend on it. But I will have an aside later on where I will talk about some additional effects which do depend more importantly on the regulator, and indeed those effects I would take less seriously for that reason. But what we'll do in this paper, and also what Roberts and Stanford did, was to keep these regulators as fixed numbers and work with them like this. So if you wanted to relate them to something more physical, you might want to study in more detail what happens if you spread over some thermal scale, et cetera, et cetera. So actually, here is the effect that is more sensitive to the regulators. So I was showing this picture before where you had the initially Lyapunov growth, and then at late times you had the quasi-normal mode decay. And actually, I should go back to the previous slide to say that if you look at this first formula here, you will recognize the quasi-normal mode decay. If you take T to be very large, so that the 1 becomes subdominant, you see some exponential behavior here. So this exponent will combine with the 2HV into some exponential decay, which is determined not just by the temperature anymore, but also by this conformal dimension of one of the operators. And that's the quasi-normal mode decay that is also encoded in this formula. You don't see it anymore when you do the 1 over C expansion, but in this formula, it's still captured. So you might have thought that you would first have the Lyapunov growth, and then it would transition into the quasi-normal mode decay. But if you actually look at this formula that I had, there is some interesting intermediate behavior, namely the decay that you see here is actually not governed by some quasi-normal mode frequencies, but this is actually some double exponential decay, which only depends on the temperature. However, here I should say that here the details of the regulator are important. For instance, if you do some time shifts in the imaginary time direction, or you do them in a real time direction and you smooth them then, you may or may not capture this intermediate behavior. So therefore, I'm not claiming that this is universal or very meaningful for that matter, but it is what you get on the nose if you take the formulas I had on the previous slide and you just plot them or study them otherwise. And then there will still be the quasi-normal mode decay at late times. But in this example, of course, you wouldn't see it because this doubly exponential, what I would call damped Lyapunov oscillations have already killed the OTOC well, to the extent that you don't see it anymore in the plot. So anyway, this was an aside. This won't play a role later in this work, but okay, I just felt it was something amusing to note. All right, so let me say a little bit about how to compute these OTOCs doing gravitational computations in an area CFT dual of the CFT. And so these are computations that were originally done by Schenker and Stanford. And the main idea is to write this out of time order correlator as an overlap of two states. So one state will be VW acting on the thermal field double state of the black hole in this case. And the other one will be WV acting on this thermal field double state. And the point is that if you look at this left state, so you have one operator inserted at is early time T3, another one at is late time T4. And because of the ordering of the operators, it turns out that this combination of both insertions is very easy to study if you propagate the insertion at T4 backward in time, and then you insert the second operator, the V operator, at the same moment of time at early times. You could, of course, propagate this state at late times, but then you would have to know how, you'd have to know the scattering amplitude before you knew the expression at late times, and that's, of course, more complicated than here. Now, if I go to the right part of the figure, because the order of insertions is different, in this case, the state takes an easy form if you display it on some late time slice. And therefore, if you compute the overlap between these two states, it's computing a scattering amplitude, a 2-to-2 scattering amplitude in gravity. And that scattering amplitude will depend on the blue shifts near the horizon, and that's what will give this Lyapunov behavior, as I will say in a little bit more detail later on. So in our work, and well, some of us had a paper like a year ago where we did similar computations in some time-dependent black hole background. So you can actually use geodesic approximation to compute this 2-to-2 scattering amplitude. So that means for all the 2-point functions or all the propagators that you see, you write them as an amplitude times some phase factor. If the conformal dimension of the operator you insert or the mass of the corresponding belt field is large enough, the variation of the phase will be fast compared to the variation of the amplitude. And you can approximate these propagators by geodesics propagating in the bulk geometry. And in a certain regime, this normalized OTOC can be written as the exponential of I times an iconal phase factor. So to compute this iconal phase, you need to know the gravitational fields from one of the infalling of one of the geodesics, and you need to know the stress tensor of the other geodesic, and then this interaction will give you the iconal phase factor, and then similarly for the other combination. So the gravitational field that is due to one of the geodesics you can obtain by solving some linearized gravitational equations, and typically the solution will be some shock wave, which often is also a solution to the nonlinear equations of motion. And if you do this exercise, you find that the iconal phase is given by Newton's constant times the Mandelstam S, so this, which corresponds to the center of mass energy. And this is given by product of masses and exponential times the surface gravity times the insertion time of the late operators minus the insertion time of the early operators. And here you see the surface gravity, which is 2 pi over beta, and that's indeed the Lyapunov exponent we had before. So that's how the computation was done for the standard thermal field double eternal black hole. So now let's, as a warm-up for the zero temperature extremal black holes that we'll be interested in, Roberts and Stanford actually, in their CFT paper, looked at the special case of an OTOC in the vacuum of a 2D holographic CFT. So we take the inverse temperature beta to be infinite. We look at times large compared to the separation of the two operators that we are inserting. And for simplicity, we take the same hierarchy of conformal dimensions between the two operators that we had before. So if you do the same exercise using the same methods, you find a very similar expression, except that the exponential growth factor that was here is now replaced by a quadratic growth in time. And if you do the same 1 over c expansion, you again get a similar expression as before, except instead of Lyapunov growth, you get this power law growth. And this was this behavior was called slow scrambling. So notice that it's a little bit subtle in the sense that if you took the exponential that was here before and you set beta to infinity very naively, you wouldn't have any time dependence left. So that's not the correct way to work. It's a little bit more subtle. The reason is that the previous expressions were valid for times large compared to the inverse temperature. And of course, here we are interested in times smaller than the inverse temperature. So you do get some growth, it's just not exponential. So some version of this slow scrambling is what one would expect for extremal black holes as well. And that's in the title of the talk. So unless there's questions about the previous parts, I will move on to OTOCs in extremal BTZ. So let me pause for a few seconds to see if there's any questions.
Can I ask one thing? Hi, Ben. I'm Roberto Temporano.
Hi, Roberto.
Yeah. So can you go back to your previous slide? Sure. So you said that you could see the quasi-normal mode decay when you had the exponentials in the previous slide. Now here, would you see something like a power law tail at late times?
Absolutely. You see it in the expression, right?
Yeah, so that's it, right? Okay, yeah. So it's the power law tail 1 over t to the 2hv. That's the usual standard power law tail, right? Instead of the quasi-normal.
I believe so, yes.
Okay, thank you.
Yeah.
I had another question. When you get hv equals hw, don't the expression simplify also, or is it just, I mean, you prefer to work in the limit hw bigger than hv?
I think, well, okay, what I know for sure is that if you have this hierarchy, you can get this expression. If you don't have this hierarchy, you could still have this 1 over c expansion, but the derivation of this expression that captures the quasi-normal mode decay or the analog thereof, I'm not sure if it would still be valid, and I actually don't think that it would still be valid.
And this is a 2D CFT which has no right movers and no left movers at all. This is just in the zero, in the, you know, in our string theory language, this is like a 2-charge, just D1D5 CFT with no momentum.
This would, I think this would be any holographic 2D CFT.
But with no momentum, with no, I mean, this is just in the ground state. So this is because, you know, when you have momentum, you expect right movers to have power law decay, but left movers to have exponential decay.
Yeah. So this is actually this is the vacuum, but so there's no left moving temperature that is non-zero or anything like that. This is just.
So for this expression, both the right moving and the left moving temperatures are 0. Okay, nice.
Exactly.
Okay.
Yes. All right. So actually, so this discussion of this hierarchy, so if we're not interested in the quasi-normal mode decay, it wouldn't be important. Then we could just have this expression and all is fine. If you are interested in quasi-normal mode decay, this is a convenient assumption to make. It may be possible to generalize it. I'm not the world expert on that, but all right. So then let's move on to the case of interest today. So before talking about extremal BTZ, which will be a maximally rotating BTZ, let's first more generally talk about rotating BTZ. So here is the metric that we'll be interested in. You see the rotation from the cross term here. So there's some outer horizon with radius r plus and inner horizon with radius r minus. The case we discussed before would be r minus equals 0, and then there would be no rotation. The case of interest in this talk will be the extremal limit where both horizons coincide, and then the metric simplifies to this expression. So in a dual CFT, as Josif was anticipating, the left moving temperature would be 0 and the right moving temperature would be r plus over pi. I don't know if there is some preferred convention between left and right here. I've seen both in the literature, so this is just a convention we picked. Okay, so this is the geometry for which we will repeat the computation we had before. So here is the Penrose, well, 2 copies of the Penrose diagram. So again, we will write the OTOC as an overlap of 2 states, and depending on the order of the insertions, the state will be easily written as an early time state, which is the case for the left-hand figure, or a late time state, which is the case for the right-hand figure. And when you take the overlap between the two, you get some scattering amplitude, this time in the extremal BTZ geometry. So to get some sense of what to expect, let's first discuss the center of mass energy, because in the previous computation is this center of mass energy, which includes the blue shifting near the horizon that gave you the Lyapunov growth. So let's see what the center of mass energy tells us in this case. So we will have an infalling almost null geodesic, and we will have an outgoing almost null geodesic. The almost null happens because we will insert our operators very close to the conformal boundary, so they will be highly blue shifted by the time they reach the interior. And imagine that these 2 geodesics will cross and therefore most strongly interact at some radius r star. So we assume that both geodesics have the same conserved energy E, and for simplicity, we take both to have 0 angular momentum. So in that case, the expression for the Mandelstam S will reduce to the product of the 2 masses, the conserved energy squared, divided by this function f, evaluated at the interaction radius r. So since we want the dependence of S on the time difference between the 2 insertions of the various operators, we need to relate this interaction radius to this time separation. And that's, of course, an easy exercise. The time difference between one of the insertions near the boundary and the interaction time will be the integral of dr divided by f of r. So here in gray, I repeated some of the formulas that we will need. So let's do the exercise of computing this time difference, this integral of 1 over f. And it turns out that there's two different regimes that are of interest. So first of all, if we take the, so let's first work in rotating BTC, so not necessarily extremal. And if we take the interaction radius to be close to the outer horizon compared to the separation between the inner and the outer horizon, then f of r will have a simple zero. And if you integrate it, you will get some logarithmic dependence on the interaction radius minus the horizon radius. On the other hand, if the inner and the outer horizon are close to each other compared to the distance between the interaction radius and the outer horizon, and this will be certainly the case in the extremal limit, of course, then you have a double pole, and the integral will give you a 1 over r star minus r plus. So if you use this to compute the time difference, or to express this f of r star in terms of the time differences, then you find that in the first regime, you get this Lyapunov behavior. So this happens to be the temperature. But in the second regime, you find a quadratic growth in time. And of course, in the extremal limit, where r minus is equal to r plus, the exponential regime completely disappears, and you will only have the power law, the quadratic growth of the center of mass energy. So, okay, so let's now specialize to extremal BTZ. So then this expression is the one that is valid. Now, in the exponential, the Lyapunov regime of the non-extremal black hole, we used to have that the Eikonov phase was proportional to Newton's constant times Mandel's time S. It turns out that in the slow scrambling regime of the that is applicable to the extremal black hole, there will be some additional time dependence beyond the delta t squared of the Mandel's time S. So let's talk about where that comes from. So first, let me remind you that to compute this, so if we do the proper computation of computing this Eikonov phase, the strategy was, well, we had these two geodesics. We compute the shock wave of one of the geodesics, and then we see how it interacts with the second geodesic. So first, for simplicity, let's imagine that the angular direction, so the phi coordinate, was decompactified. So in the geometry that we're interested in, phi is a compact coordinate with period 2 pi. But let's first decompactify it for simplicity, because then the shock waves take a reasonably simple form. So in orange, there would be a geodesic. The details of the figure are not so important, except that the boundary is like in the front of the slide, so to say, so towards us. And what you see is that if this is an outgoing geodesic, the shock wave corresponding to it is emitted towards the boundary. Now, if we take into account the periodicity of the phi direction, then you can compute a shock wave in that compact geometry by using a method of images, if you wish. And then, well, on the left figure here, you have some contour plots of the Eikonov phase, where the contours are chosen in such a way that if they are equidistant, it's like it corresponds to a cubic growth, for reasons I will mention later. But if you take into account the compactness of the phi coordinates and therefore the method of images, so this left figure is like the bottom in the middle of the right figure. So here we added some virtual regions on both sides that correspond to the image sources. And this gives you a more intricate pattern And so, for instance, if you wanted the time dependence at some fixed spatial separation of the operators, you would need to make some vertical slice in this figure. I will show it to you later. And if you want the spatial dependence at some fixed time difference between the operators, so you want the spatial dependence as the insertion points are varied in space, you need to take some horizontal slice. So let me first take the horizontal slice and show you the result. So this is the spatial dependence that you would get. So you see a periodicity of 2 pi, and the cusp is chosen to be at minus pi and pi. So this is a periodic, so there's the cusp there. But because of the periodicity, it's not a simple decay on both sides because the profile has to go up again in order to be periodic. So this is the spatial dependence of the shock wave in this for this compact phi dimension. Now, more important for us will be the time dependence. And this is the results if you do the computation, take into account the images. And so let me walk you through this, this plot. So this is the iconal phase factor, which will determine the OTOC as a function of the separation between the 2 pairs of insertions at the boundary of this out of time order correlator. And you see that, well, the actual plot is in blue. And you see that it's well approximated on average, if you average out the wiggles, by this average orange line, which is approximately a cubic growth. So there's some wiggles on top of that. So that's, I'm calling a sawtooth pattern. And actually, instead of having everywhere cubic growth, it's actually the average cubic growth is a succession of some brief phase of quadratic growth, and then an even briefer phase of exponential growth. And they alternate, and in such a way, after the quadratic growth, there is some fast exponential growth to catch up with the average cubic growth in the figure. So let me comment on that figure. Was there a question? Okay, maybe I'll first make the comments and then we can see if there's anything still not clear. Okay, as I mentioned already, because of the periodicity of phi, we obtain the shock wave using some method of images. And importantly, here is that the number of images that contributes is proportional to the time separation delta t. And that's actually a consequence of causality. So you can imagine that the 2 geodesics can either interact directly, or one of them could circle the black hole a few times and then interact with the other one. Or you could imagine that it's the shock wave that goes around the black hole a few times and then interacts with the second geodesic. But the number of times you could have circled the black hole depends on the time separation, and you can check that it's proportional to the time separation. And so therefore, the cubic growth we saw in the previous plot is the product of the quadratic growth we had before of the Mandelstam S that you would have in a non-compact situation, times the number of images that contributes, and that gives a factor of delta t. So and they combine to the delta t cubed. So this local quadratic and exponential growth actually reflects the left and right moving temperatures that Josif was talking about before. And this you can see very cleanly in the limit that the right moving temperature is large. And another comment to make is that for delta t small compared to the inverse temperature, which will of course always be the case for extremal black holes, where beta is infinite, the scattering happens away from the horizon. So in previous discussions of at finite temperature, where you were interested in long time intervals compared to the inverse temperature, people had replaced the shockwave profile by the profile at the horizon. It turns out that if you do that in our computation, so if you make the approximation of replacing the shockwave by the shockwave at the horizon, then you would get infinity. Because if you replaced it by the shockwave at the horizon, it would correspond to taking an infinite time interval, and then an infinite number of copies would kick in. And since each of these copies contributes some delta t squared, shifted somehow, that would give you an infinity. So that doesn't work in this case. So in this case, it's crucial that you do the computation taking into account the precise profile of the shockwave, not approximating it by some profile at the horizon, and then you find a nice and finite result. And I should also say that a similar sawtooth pattern has been observed before by Mazet and Sharoshi for non-extremal rotating black holes in the regime where delta T is large compared to the inverse temperature. Of course, in that case, there was always exponential average growth, not power law growth. And there had also been some previous work on non-extremal rotating black holes, which was more focused on saying that there would be two possible behaviors. But to my knowledge, is the paper of Mazet and Sharoshi that put the ingredients together, took into account the periodicity, and then found this average growth that is determined by the slowest growth rate. So the smallest Lyapunov exponent in their case, in our case, is the power law growth.
Sorry, Ben, can I ask a very elementary question?
Sure.
Yes. So as far as I remember in the old works by 't Hooft, when he was doing the computation of shockwaves in asymptotically flat spacetimes, the S matrix that you get is unitary, right? Your phase is a pure phase that you get from this computation.
Okay.
So can you compare this to the result that you have now? I suppose is the information coming back in your computation, or somehow you are, what is the result? You compare it with these old works. Because this is a near horizon effect, right? It does not have to do with asymptotics.
Right.
And then you can glue it to whatever asymptotics you want. But, yeah.
Yeah, so I agree that this shouldn't be dependent on the asymptotics as far as I know. I don't have a more complete answer ready at this point. Maybe we can discuss it afterwards if you want.
Okay.
I don't have an answer right away.
My internet connection is a little bit funky here, but can you say more about how the left moving temperature and right moving temperature create the exponential and the power law growth? I mean, if you're in the ground state, you expect the power law growth, and if you're in the encountering the thermal particles on the right moving sector, then you expect the exponential growth there. So I guess my expectation is that if the probe or something to do with the geodesic is left moving versus if its component has a right moving component, it encounters or doesn't encounter the thermally excited states. Is there anything you can say about that?
Okay, I don't know if I have a full answer to your question, but I can say a few things. So one is related to the computations we've done here. So from a gravity point of view, the behavior of the shockwave is rather different on the left and the right of the geodesic. So one of the two fall-offs will be exponential, set by the right moving temperature. Sorry, that's this one. The other fall-off is quadratic, and that's set by the zero left moving temperature. And then those things add up from the images, and that's how the exponential emerges from a gravity computation. I can say a little bit about the CFT computation. That's actually some work in progress I'm doing with Surbik et al, and I'll mention a bit about that at the end of the talk. So there, you can do a computation using the same methods as Roberts and Stanford, as I mentioned before. And there, depending on the spatial separation and the time separation, so depending on which regime you are in, the growth will dominantly come from either the left or the right movers. And so if you're at any given point in the situation with a compact circle, you will get contributions from both, but depending on where you are, one of the two contributions will dominate.
What sets the crossover? What sets the crossover between the domination of the left movers and right movers?
It was well, okay, I can tell you technically, if you, in these extremal BTZ geometries, you can go to some coordinates, some angular coordinate that is co-rotating at the horizon. It's when that co-rotating coordinate is 0, meaning at the same position as the insertions of the boundary operators. So if you're to the left of it, you get one behavior. If you go to the right of it, you get the other behavior. And technically that had to do with, in order to get these out of time order correlators, you have to go around some branch points to go to some second sheet in CFT. And depending on the details of where you are, it will be either the left or the right movers that pick up some contribution from going around the branch points. Yeah, probably too quick to absorb in detail, but
hi, I had a question. Can I?
Hi, Ron. Yes.
Yeah. So hi. Just to elaborate on Nicholas's question, if you're comparing whatever is the answer that you get in the CFT in extremal in an extremal setting, if you expanded your OTOC to 1 over C, and you had an expansion of 1 minus whatever is the object that you get, probably it would be an exponential. So in the extremal limit, do you find an exponential in the extremal CFT state contributing? If you just expanded it to
yes,
okay, and that would be the non-zero temperature.
Yes, exactly. So, well, again, the details will appear hopefully soon. But if you take, for simplicity, if you take the CFT on the line, so the spatial, if you decompactify the spatial circle, you get some exponential growth at early times, and you get the power law growth at late times. Again, it's an extrapolation of the kind of behavior in Mezei and Sharoshi. They also looked at the decompactification limit at some point. And then if you go to the compact circle, it becomes a bit more complicated. And there we're still filling in the last details, but that's what you get indeed, yes.
Just to understand clearly the graph that you have drawn with the sawtooth, the blue and the green stuff. So if you were to ask right close to 0 where everything looks flat, where the competition between leading and subleading mode is happening, the first behavior that you get as far as your CFT computation informs you will tell you that that thing is exponential in nature. And then you get this sawtooth. Would that be right?
Well, I guess that depends on the spatial separation of the various insertions, where exactly you start on the curve. But it will certainly be some alternation between quadratic and so yeah. So here we're always below the average curve, right? So here.
Okay.
Yeah.
So,
okay. I think it's.
Yeah.
For the question about the initial growth, wouldn't if you started on the left of the particle, it would start with a sort of quadratic growth, and if you started on the right of the particle, it would start with exponential at the earliest times? Isn't there this transition depending on which side you start on?
Yeah, and starting at the left or the right means like what is the spatial separation of the early time and late time insertions, right? Is that correct?
Yeah, sorry, that's what I should have said. Yeah, this X.
Right. Yes. So you can sort of choose where you start on the figure. What is certainly true is that you get this alternation between very brief periods of left and right, and then they combine into this average cubic growth. And this is what will determine the scrambling time, right? Because you have this huge 1 over C factor to overcome. So after you've had many of these oscillations, this small correction factor will overcome the constant, and that will give the scrambling. At least that's a picture that we have. But okay, I should probably move on so that I can say something about the. Well, okay, so the comments I've made, I think. So let's move on to the microstate geometries. So, okay, this being Paris, quite a few of you know these geometries much better than I do. For those who don't, all you need to know is in this figure. So if you followed these dashed lines, you would have an you would have an extremal BTZ geometry with a singularity down an infinite throat. These so-called 1,0n superstrata are very nice microstate geometries that have a very deep but not infinite throat, which is then kept off smoothly before there would be there would be horizon, sorry, of the BTZ black hole. So there's two parameters, A and B, and also this n that appear in the solution. There is some radial coordinate, which is rho in the coordinates used in this metric. I won't say any details about them, but there's two important values. One is the radial coordinate where you have the transition between the asymptotic ADS3 regime and then the ADS2 times S1 throat that you would also have in BTZ. And importantly, this throat can be very large in these microstate geometries. And then there's a second radial coordinate, which I call rho cap here, which is where you have the transition between these throats and the cap region. And if I took this parameter A to 0, I would find the black hole limit of the geometry. So these are geometries that have ADS-CFT duals in the D1, D5 CFT. You can think of them as some coherent superpositions of some explicitly known states of the CFT, which has some large central charge determined by the product of numbers of D1 and D5 branes. The details don't matter for our purposes. These solutions are BPS, so they correspond to BPS states in the dual CFT, and they can be constructed at the symmetric orbifold point, where these constructions are easier than generic points, of course. The way to construct them, well, some of the experts are in the audience, but the idea is that you start with two charge solutions, just D1, D5 without momentum. But then you apply some method to it which reduces the angular momentum of the solution and increases the momentum, and that you keep doing until there is a lot of momentum and not much angular momentum left. And this angular momentum and momentum are quantified by these parameters A and B that parameterize the geometry. So for our purposes, what do we have to do? Well, again, we will compute an OTOC, so there will be two operators inserted at early times near the boundary, two operators at late times. This is a spatial slice, of course, of the geometry. We are interested in the time difference of the insertions such that the interaction happens at this transition between the asymptotic region and the throat. We're also interested in the time separation of the OTOC such that the interaction happens at the cap region. And then what you would expect is that if this interaction happens outside the cap, that the result should be very closely approximated to the extremal BTZ result. If the interaction happens in the cap region, there should be significant deviations. That's what one would expect a priori. And notice that there is this large hierarchy between the throat and the cap time separations given by the product of D1 and D5 charges, which is essentially the central charge of the CFT, and therefore a large number. So, okay, so this you can all compute. And the important thing is that for large time separations, the quadratic growth of the center of mass energy, or the Mandelstam S, stops as the interaction reaches the cap region. And here it saturates, and then later on it will bounce back to the exterior of the cap. So that's one effect. A second effect is that because of the cap, the shock waves that we computed in extremal BTZ will also be modified. So as long as the interactions happen outside the cap region, it should still be an excellent approximation to use the BTC shock waves that we have. When the interactions reach the cap region, then the detailed form will depend on shock waves in 6D superstrata geometries. We haven't computed them. We suspect it might be possible to compute them because, well, in particular, the group at Saclay has done quite a number of detailed computations in these geometries. So we suspect it may be possible, but okay, we haven't done it. I guess it also depends on how crucial it is to know the details in this OTOC. And then there's one more effect that I wanted to mention, and that's the effect of tidal forces, which also goes back to observations by the group at Saclay, which is the following. So the geodesic approximation that we've been using, as I've mentioned before, is to approximate 2-point functions by an ansatz like this, where the phase S is given by a geodesic length. So K is the velocity of a geodesic. And the validity of this WKB or geodesic approximation is that the amplitude should vary slowly compared to the phase. So if you contract this with the velocity k mu, you find a condition on the time derivative of the amplitude, and one can compute that this is given in terms of the volume expansion theta. And so a necessary condition for WKB to be valid is that this theta should always be smaller than the mass of the bulk field that corresponds to the conformal dimension of the operators in the CFT that we're inserting. Now, the time dependence of this theta can be computed from the Ray-Chaudhuri equation. We haven't fully done it, but we have observed that there is this last term that comes from the curvature. And this last term consists of 2 terms. The first one is already present in extremal BTZ. And we know in extremal BTZ things should be fine. But then there's the second term, which will be subdominant close to the asymptotic region, but it will grow and overtake the first term as this radial coordinate rho gets smaller and smaller. And this second term will grow and it will invalidate the geodesic approximation from a certain time separation T tidal onwards. I'm not going to do the computation here, but here is the result. So we ignored these other terms that are already present for BTZ, and we've just isolated this one contribution to the right-hand side, and we've seen if we took that contribution in isolation, when would it invalidate the approximation? And then we're extrapolating that, well, even in the full computation, one might expect that at a similar time, the geodesic approximation will stop being valid. So, of course, then we have to see how these various timescales that we have compared to each other. So I will list the results here. So first of all, the delta T cap, when the scattering would happen in the cap region. So here is the ratio between that and the scrambling time. And you see on the right-hand side that all the contributions or almost all the contributions try to make this a big number. The conformal dimensions are big, and 1 is big, and 5 is big. Epsilon is the holographic regulator. So 1 over epsilon is the radius where you insert the operators. So that's small. So the only thing that could make this small is the right moving temperature, if that was taken to be huge. But if not, then one expects that this is a huge number, and therefore the cap will only show up after the scrambling time. So that means the whole scrambling process in these 1, 0, and superstrata microstates has been completed, or at least the Lyapunov growth, and then there's been the saturation before the cap region kicks in. What we don't have access to in our geodesic approximation is the late time quasi-normal modes decay. So how that compares to the cap time that we don't have access to with the methods we've used so far. So then when do the tidal effects kick in compared to the scrambling time? Well, it's a similar story. They will only be important before the scrambling time if the right moving temperature is huge. So normally one would expect that the Lyapunov, well, the analog of the Lyapunov growth, which is cubic growth in our case with a sawtooth pattern, that the growth can complete itself. You can get to the maximum before you will notice the tidal effects. So the conclusion from this would be that for the purposes of following the analog of Lyapunov growth until saturation in these 1,0 superstrata geometries, they will mimic what extremal BTZ does, except for extremely high right moving temperatures. And from what we could tell, there doesn't seem to be an obvious upper limit on what that right moving temperature could be. So I guess one could probably engineer regimes where you would see effects of the cap or of the tidal forces.
Could I make a quick comment on?
Sure.
Yeah, so I just want to say that this is actually in accordance with the paper Emil and I just put out there. The tidal forces get large, but what happens is they have very, very short period of time to act. And so the time it takes to get to for the probe to get to the cap is extremely short. And so the net impulse of the tidal force remains small. So your approximation is reliable all the way down to the cap. Once you hit the cap, you're in trouble. But generally speaking, the scrambling is not significant until you hit the cap. The other comment I was going to make also is, I notice you're using the Ray-Choudhury equation, which is a volume measurement. The thing for the tidal forces is, of course, the individual eigenvalues, some of which are positive and some which are negative. And I was messing around with some other examples where the Ricci tensor doesn't see any of these eigenvalues because there are large positive and large negative eigenvalues. They cancel out, leaving you with essentially a small Ricci tensor. Presumably you would expect a problem if you actually looked at the eigenbasis of a Riemann tensor rather than just the volume Ray-Choudhury equation.
Yes, that may well be. I think, okay, my collaborators can correct me if they know more than I do, but so far we've looked at this component, and that's indeed, there is room for additional issues if you look at individual components. But I see Charles showing up, so maybe you want to say something, Charles?
Yeah, I could just make a quick comment on that. So in our case, the component that's important, I think, is if you go to one slide back, it's that particular component where you take the Ricci tensor contracted with the tangent of the geodesic that's falling in. So it's actually a particular scalar that is important, right, for the calculation we're doing. And so it's not, we're not just looking at some large eigenvalue or something. We're taking like the tangent contracted into the Ricci.
So that's why you're taking the volume. The Ricci tensor is the sum of the eigenvalues of the tidal force in some sense, and so therefore it gives you the volume expansion rather than.
But the volume expansion is the relevant quantity.
You have a number of different components here, right?
Yes, exactly. So I would assume that the components that you have in the amplitude could be directionally dependent, and that so when you spaghettify something, usually there's huge compression in one direction and stretching in another direction. And in very bizarre circumstances, the stretching and the expansion stretching and compression can cancel each other out so that the Ricci tensor doesn't see it. So what's happening is you drop in something that's spherical and it becomes a very flat ellipse of the same volume.
Yeah, so there's like there'll be the shears will get large or something instead first.
One eigenvalue is positive in the Riemann tensor, it stretches the hell out of the thing, and one eigenvalue is negative, which compresses the hell out of it, or vice versa. And as a result, the volume doesn't actually change very much compared to BTZ. So this fact that there's an uncancelled a squared b cubed over rho to the sixth term, there are sort of some examples I have where that's actually suppressed in the Ricci tensor, but in the Riemann tensor, there's big terms like that. So I'm guessing your AXY has some structure which perhaps violates the approximation, but you won't see it in the volume term. Anyway, just a comment, really.
Yeah. Thanks. I wanted to comment on the first thing you said, Nick, about the effect of tidal forces sometimes being small. I think it's a distinct thing from what I've been saying, because in our case, they don't kick in because you never reach the region where the tidal forces are present. So I think what you are saying is, I think what you're maybe implying is that even if you went to even larger timescales so that you do reach the interaction region where the tidal forces are present, it might still not kill the approximation. Is that what you're saying?
Yes, exactly. Emil and I dropped in a string probe, and you find the string gets excited in the tidal region, but the excitation, the time for infall from that region to the cap is very, very short, and as a result, the string excitations are of order 1. So you can still use, roughly speaking, a massive geodesic approximation on that string. So originally I thought that all hell would break loose at the tidal region. It doesn't. It's actually still a controllable approximation all the way down to the cap. Okay, that's excellent. That's excellent news, actually, because that would mean that if we took the time separation large enough, and if we take the right moving temperature to be huge, I mean, I don't know if there's a limit to what one can do there, but I'm assuming for now that that it's just some free parameter. Then one could actually start probing the cap region, one could hope. I think you can begin to probe the transition. There's this very bumpy region where you transition from the throat to the cap. That region, I think you can begin to probe. Once you get beyond that, I think you're beginning to really rip the guts out of the probe particle. Okay. Okay, so thanks. Let me just end with some discussion. I mentioned already that it's possible to reproduce this sawtooth pattern using CFT computations. That's work in progress right now. There is an important subtlety, though, which is that for low enough temperatures, BTZ actually does not dominate the canonical ensemble. And that's in particular the case at 0 temperature, which is relevant for extremal BTZ. So therefore, the gravity computation that we've been doing in extremal BTZ should actually not correspond to a thermal OTOC in the CFT, because the dominant saddle should correspond to a thermal gas in ADS rather than to a black hole. So you might be worried that, okay, what does this mean? What is the status then of this gravity computation I've been telling you about? Well, one is not obliged to do thermal computations in the dual CFT. I've told you that these microstate geometries are dual to some specific CFT pure states, and one can choose to compute an OTOC in some coherent combination of these states that one knows to be dual to microstate geometries. So from that point of view, the BTZ computation we've been doing is not justified by computing some thermal correlation function in the CFT, but it is justified as a good approximation to the OTOC in the states corresponding to microstate geometries. So that's just a comment on the dual CFT and the status of this bulk computation. So let me then just summarize, because my time is up in the meantime. So the Lyapunov behavior of OTOCs for non-extremal black holes corresponds to gravitational scattering near the horizon. So I've mentioned that the OTOC can be computed using a geodesic approximation. And if you do that for extremal BTZ, you actually find that the gravitational scattering happens away from the horizon. You would get nonsense if you approximated the shock waves by those on the horizon. So this leads to slow scrambling and an OTOC that displays a sawtooth pattern. If you do the exercise in microstate geometries, you reproduce the slow scrambling properties of extremal BTZ. There are deviations that kick in after the scrambling time, except if you work at extremely high temperatures. So that's all I have to say. So thank you for listening.
Okay, well, thank you very much for the talk, Ben. We have plenty of questions during the talk, but well, of course, there's time for more questions. So,
just a very quick question. So, in the microstate geometries, do you see that really cool oscillation exchange between quadratic growth and exponential growth, exponential growth that averages out to the cubic growth?
Yeah, yes, it's exactly the same. So if you so the OTOC in the microstate geometries, unless you work at these huge temperatures where the cap or the tidal forces might kick in, but if you work like at normal temperatures, let's say, you will find an exact copy of what I showed you in the extremal BTZ.
And what happens when you hit the tidal boundary? Does it just continue on through, or do you see something?
Yeah, that we haven't checked. So what you do know is that the quadratic, so the cubic growth was a product of the quadratic growth from the center of mass energy, and then the linear growth in time from the number of copies. So what certainly caps off when you reach the cap is this quadratic growth. So that's so instead of growing quadratically, that will cap off, and then I guess it should reduce again, because if you wait long enough, the interaction, okay, if you, as you increase the time separation of the insertions, your interaction will go closer and closer to the cap. But then at some point, I would expect that it will move back towards the exterior. But we haven't tracked that. So what we've done so far is just estimated timescales where some effect of the cap or some effect of the tidal forces would kick in. But then computing in detail, like what exactly the effects would be, that we haven't done so far.
Okay, thank you.
Any further question?
I have a question about this BTZ not dominating the ensemble. I mean, I'm a bit confused. So why do you say, so low enough temperature, this is low enough right moving temperature, or low enough total temperature?
Total temperature.
Total. And who is dominating the ensemble then? Because,
thermal gas.
Oh, but wait, I'm confused. I mean, in the D5P system, for example, if I have a supersymmetric black hole, that's dominating the ensemble. That's giving the Strominger-Vafa entropy. And that's a BTZ of like 0 temperature. I think it's low enough for a right moving temperature.
Well,
the graviton gas, the thermal gas only dominates in a very specific regime, but it doesn't dominate in general. I mean, for no range when the horizon is big, the graviton gas dominates. This I know because, we've been trying superstrata graviton gas. So, essentially, we've been trying to understand how much entropy superstrata have and when do they dominate the ensemble and so on. And the answer is more or less never. I mean, never in the regime when the black hole has a big enough horizon.
Okay, that I'd be happy to discuss. I know in this paper by Mezei and Sharoshi, they give this, they say that for low enough temperature, the black hole does not dominate the ensemble anymore. I think the original reference was a paper by Hartmann and others. But I'd be happy to discuss this further. I don't know it in full detail. If someone else wants to comment that maybe has looked at the papers.
There are some guys arguing that there are some Euclidean images or something, but those are not. I mean, in Minkowski, they're not. I don't think in Minkowski anybody dominates. I think the BTZ is the only guy. I mean, again, this is Strominger-Vafa. I mean, Strominger-Vafa is hopefully dominating the ensemble, and it's matching the entropy from the bulk from the CFT, and that's BTZ at 0 temperature. So I think there should be some confusion about. There's some confusion about something. But
so the alternative is thermal gas and ADS, but
thermal gas and ADS is superstrata. We know very well.
I know. I was about to make exactly that point. More the point. Thermal gas and ADS is not back reacted. If you take that thermal gas and back react it, you'll probably find that it's a superstratum. So I don't think it's actually inconsistent with that the whole microstate geometry program. It's simply if the alternative is the thermal gas and ADS, then if you back react it, it has to be some kind of microstate geometry.
But we know that thermal gas doesn't count the black hole entropy. This is what Masaki and Daniel Meyerson just showed, last week, and and also Masaki showed before. So if you count thermal gas, you basically count L-1s on the CFT. You don't count fractional L's. So you should count L-1 over C L sub minus 1 over C. Those are the ones, the fractionated modes, they're the ones which give you the black hole entropy. And thermal gas is just L minus 1s. So L minus 1s don't give you enough entropy. So
we don't know what.
Okay, this is definitely something I would like to understand better, because there are these claims that
Can I just interject
it
one?
doesn't dominate. So yeah, okay, Charles.
One quick comment. I think there might be a difference between doing like a 3D gravity computation and a 10D computation. I think that might be part of the issue.
Oh, 3D gravity.
I don't know
Supposed to do 3D gravity.
Yeah, I think these comments about not dominating, I think might be in like some bottom-up 3D gravity perspective.
Okay.
Now you've just told Jose to rise the whole thing off.
Good.
Sorry, guys.
I think in the 10D case, I think then you can believe it or something. But then.
Okay. No, thanks. We can discuss afterwards. So.
Thanks, man. I gotta go.
Okay. Thanks, Nick. Bye.
Well,
can I ask a quick question? Sorry.
Sure. Go ahead.
For your results for the outer time order correlator in the microstate geometry, can I make any interpretations as in terms of the Regge limit of some 6-point correlator with two heavy operators that correspond to the microstate?
I think so. You could think of the black holes or the microstates as being created by some heavy operators, and then within that state you create it in that way, you would compute the 4-point function, the OTOC. So taking everything together, it would indeed be some 6-point function in vacuum. Yes.
Oh, thank you.
Well, okay. I think we had several questions, so I think we can thank Ben again. So
thanks a lot.
So yeah, I think we can conclude the talk. Thank you very much for the